Hello everyone. In this lecture, we will look at dates and times. Now, dates and times seem very simple, and it doesn't seem like there would be a lot of confusion around it. But there are some questions that you should ask yourself. Does every year have 365 days? Does every day have 24 hours? And does every minute have 60 seconds? Now, you know that there is the concept of daylight savings time, which means that some days have 23 hours and some have 25. And obviously, leap years will have an extra day in it. And you might not have known that some minutes have 61 seconds because every now and then leap seconds are added since the Earth's rotation is gradually slowing down. And this is why dates and times are hard. Because you have to reconcile with two physical phenomena, which is the rotation of the Earth and the orbit around the Sun. There is an entire series of geopolitical phenomena, including month, time zone, daylight saving time, that you have to deal with. Now, the attempt of this chapter is not to teach you about each and every small, minute thing related to date and time, but to give you a solid understanding of practical skills that you will have to use while solving common data challenges. For this lecture, we are going to look at the library called Lubridate. This makes it easy to work with dates and times. Now, this is not a part of the core tidyverse since we only need it when we're working with date and times. We will also take our NYC flights 13 dataset, something that we've already worked on. Now, there are three types of date time. We have a date, we have a time, and we have a date time value. Now, in this chapter, we will focus on dates and date time, since R does not have a native class for storing the time value. There is a package called the HMS package, but let's leave that for now. Now, if we simply want to get the current date, I can use today and I can use now to get the date and the time. Now, date time data sometimes comes in the form of strings. Now, one approach is to parse the string as a datetime value, and another approach is to use the helpers provided by Lubridate. Now, these will automatically work out the format once we specify the order of the component. Let's take some examples. As you can see, when I specify the order YMD, MDY, and DMY, we get the correct three results. Now, these functions also take unquoted numbers. For example, if we simply write YMD followed by an unquoted number like this, we still get the result. Also, if I want to create a datetime value, we can do that as well, like this. Or we can create a datetime value like this. We can also force the creation of a datetime from a date by supplying our own time zone like this. So instead of a single string, sometimes we will have individual components of the datetime spread across multiple columns like we have in the flights dataset. To create a datetime from this sort of input, we have to use make date like this. Very simple. It gives me the complete date. Now let us do the same thing for each of the four time columns that we have. Now the times are represented in a slightly odd format. So we have to use a modulus arithmetic to be able to pull out the hour and the minute components. Let's see. So this part is a little long. Please make sure to practice this properly. We are creating a make daytime like this with the modulus, and we are using an object flights dt. Let's go through it line by line. We have done most of these things earlier, and the result would be like this. With this data, we would be able to visualize the distribution of departure times across all the years like this. We can also do this for a single day like this. Remember, 1 means 1 second. So bin width of 86,400 means 1 day, because there are 86,400 seconds in a day. If we want to switch between a date time and a date, we can do it like this. And we can also do this with the now, like this. And sometimes you will get the date time value as a numeric offset. It doesn't happen very commonly, but if it does happen, then just keep in mind you can do this. Or for that matter, one more example like this. Now remember, this is the Unix epoch, which is 1/1/1970, right? That's why the results are coming like this. So now that we have seen a little bit of the date time structure, let us explore what all we can do with it. So we can pull out different paths with the year, month, M day, Y day, W day, hour, minute, second. All of this is fairly simple, as you can see. We can just pull out different paths like this. For the month and the W day, we can also set the label equal to true, right? Which will return the abbreviated name of the month or the day of the week. And if we want to return the full name, we will set the abbreviation to false. We can also use the WD to see that more flights have been departing during the week than on the weekend, as is very clear in this chart. So there is an interesting pattern if we look at the average departure. In fact, if we look at the average departure delay, there is an interesting pattern by the minute within the hour. So it looks like flights leaving in minutes 20 to 30 and 50 to 60 have much lower delays than the rest of the hour. Watch this. Right? So 20 to 30 and 50 to 60. And interestingly, if we look at the scheduled departure time, we don't really get this strong pattern. If you see this, we don't really get such a strong pattern. So why do we see that pattern with the actual departure times? You know, just like most data collected by humans, there is a strong bias towards flights leaving at a nice departure time. And probably that's the reason we don't see those values. So always be careful about this wherever there is an element of human judgment involved. An alternative approach to plotting individual components is to round the date to a nearby unit of time, and for this we use floor date, round date, and ceiling date. Let's take a few examples. Here we're using flow date like this. And computing the difference between a rounded and an unrounded date can be particularly useful. Okay, after this, what else can we do? We can also use each accessor function to set the components of a date time. So we're using accessor functions here. And alternatively, rather than modifying in place, you can also create a new date time with an update, which would be like this. And if the values are too big, they will automatically roll over. So you can use the update to show the distribution of flights across the course of the day for each day of the year. Like this. And setting larger components of a date to a constant is a very powerful technique which allows you to explore patterns in the smaller components. Next, we will look at time spans. So we look at subtraction, addition, and division. So there are three important classes that you have to keep in mind. So we have durations, periods, and intervals. So in R, when we subtract two dates, we get a diff time object like this. So a diff time class object records a time span of seconds, minutes, hours, days, or weeks. But this ambiguity can make this a little difficult to work with. And that is why lubridate provides an alternative which always uses the second. And this is the duration. How does that look? Like this, very simple, as duration. Now durations comes with a bunch of convenient constructors. I'm giving you a number of examples here like this. We have these seconds, minutes, hours, days, weeks, and years. Durations will always record the time span in seconds. So larger units are created by converting minutes, hours, days, weeks, and years to seconds at the standard rate, which is 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 7 days in a week, and 365 days in a year. We can also add and multiply durations, and we can also add and subtract durations to and from days like this. However, because durations are representing an exact number of seconds, sometimes you might get some unexpected results. As you can see, why is one day after 1 p.m. on March 12th, 2 p.m. on March 13th? Now, if you look carefully, you might also notice that the time zone has changed from EST to EDT. And because of daylight saving time, since March 12 only has 23 hours, if we add a full day worth of seconds, we might end up with a different time. So you have to be careful about this. How do we solve this problem? By using periods. So periods are time spans, but they do not have a fixed length in seconds. They instead work with what we call human times, like days and months. And this makes them more intuitive. So we are working with periods now. These are much more intuitive. As you can see, we get the correct result. And like durations, periods can also be created with a lot of constructor functions like this. We have seconds, minutes, hour, day, month, week, and years. We can also add and multiply the periods. And of course, we can also add them to days. So compared to durations, periods are much more likely to do what you expect. As you can see, correct result. Now we will use periods to fix something very odd in our flight data, where some planes appear to have arrived at the destination even before they have departed from the city. Now, how is this happening? These are overnight flights. So we've used the same date information for both the departure and the arrival time, but these flights have arrived on the following day. And we can fix this by adding days, which is 1, to the arrival time of each overnight flight, like this. And once we have done that, now the result will make much more sense. It will now follow the laws of physics and the result will be correct. And now we come to intervals. It is obvious what D years and D days should return, because durations are always represented by a number of seconds. A duration of a year is defined as 365 days worth of seconds. But what should years 1 and days 1 return? See, if the year is 2015, it should be 365 as a result. But if it is 2016, it should return 366, right? Because it's a leap year. Now, there is not quite enough information for lubricate to give us a single clear answer. So what it does is, it gives us an estimate with a warning. Let's see. Now, if I want a more accurate measurement, we have to use an interval. So an interval is a duration with a starting point that makes it precise, and we can determine exactly how long it is, like this. And to find out how many periods fall into an interval, we have to use the integer division, which would be like this. There is a question that how do you pick between duration, periods, and intervals? Now, as always, you pick the simplest data structure that solves the problem. So if you only care about the physical time, you use a duration. And if you want to add human times, you use a period. If you need to figure out how long a span is in human units, you use an interval. Let's look at a summary that will explain this entire thing. So here you can see it has been summarized as to which one you should use. Excellent. So that completes our complete section on data wrangling. And in the next lecture, we will look at program. And in that lecture, we will look at how to improve programming skills.